Hello everyone, welcome to my channel. So in the previous video, I showed you clusters of CPI, the Consumer Price Index. So here's what we saw in the last video. This is called a dendrogram. And we can get this if we do hierarchical clustering. So clustering is grouping. And in the context of time series, clustering for time series is grouping similar time series together. Now, there are two types of hierarchical clustering. The first one is divisive and the second one is agglomerative. In this video, we're going to focus on the agglomerative clustering. More specifically, we will try to understand the algorithm with different representations, and then we will also discuss several types of linkage. A linkage is a very important concept in clustering. And finally, we will apply this, so we will cluster the CPI fluctuations using sklearn. We will see how a different linkage would lead to a very different looking dendrogram. Okay, so let's study together. The agglomerative clustering is also called the bottom-top clustering because we start from the bottom, where all observations are seen as distinct clusters, to the top, where these little clusters are merged into a bigger group. Now let's see a very simple example here, where we have only 5 observations and 2-dimensional feature space, and this here is the leftmost picture here is the raw representations, and looking at it visually, we can see immediately how the clusters are formed, right? So if we want to have 2 clusters, then the first cluster would include A, B, and C, and the second one would include D and E. But let's see how the agglomerative clustering algorithm finds these clusters. Okay, so there are 2 things about agglomerative clustering algorithm. The first one, its input. We need a distance matrix before we begin. So this matrix here is the distance matrix. A distance matrix stores the distances between pairs of observations. Since we have 5 observations, our distance matrix is in 5 by 5. Okay. The distance matrix is a symmetrical one because the distance from A to B must be equal to the distance between B and A, right? And then its diagonal must be 0 because like this, row A, column A means we are calculating the distance between A and itself, and it must be 0. That's the first thing. The second thing is that this is an iterative process. So we start with all observations seen as a cluster on its own, and then we will stop when we have 2 clusters. Well, actually, we can modify it. We can stop when we have 3 or any number of clusters, but the default is 2. Okay, so let's start from the first iteration. Here is the state of the first iteration. Next, in the first iteration, we need to build a distance matrix, another distance matrix. But this time, we build a distance matrix between clusters. Okay, so that will happen in each iteration. But here's the thing. In the first iteration, we see all observations as distinct clusters. So actually, the distance matrix between clusters is exactly the same as the distance matrix between observations, right? So we can just copy this and paste it to the right. And now we can focus on the matrix on the right side. Okay, so the matrix on the left side is the distance matrix between observations, but on the right side, it is the distance matrix between clusters. Yeah. And now, here's the important thing. In each iteration, once we have the distance matrix between clusters, we need to find its minimum. In other words, we need to find 2 closest clusters and merge them together. Okay. Visually, on the left side here, we can see clearly, immediately that D and E are clustered together, right? And we can verify this on the matrix with a matrix that 0.5 is the minimum. Let me color it differently. So 0.58 is the minimum, and it's the distance between D and E, or E and D, if you will. And yeah, at the end of the first iteration, we have 4 clusters now. Cluster A, cluster B, cluster C, and cluster DE. Okay, I said DE together. So yeah, cluster DE. Okay, so that's it. That's it for the first iteration. Now let's move on to the second iteration. In the second iteration, now we have 4 clusters. So when we want to make distance matrix between clusters, now we only need to make it 4 by 4. I'll just make it very roughly here. And the rows would be A, and then B, C, and then DE. And the same goes for the columns. Well, to fill this part of the matrix, to calculate the distances between cluster A, cluster B, and cluster C, it's already exactly the same as this part of the distance matrix, right? So that part is done. But now we still need to fill in some cells, right? Of course, this part is 0. Let's say that we want to know the distance between B and DE, the cluster B and cluster DE. How can we do that? So this is the right time to talk about linkage, okay? But first, we need to calculate the distance between B and D and B and E. Okay, the distance between B and D is 3.72, while the distance between B and E is 4.3. Okay, now we have 2 values, right? Basically, if the bigger cluster, so if cluster DE has 5 members, then we need 5 combinations. Okay, so basically combinations of each observations in both clusters. Since cluster B has only 1 member and cluster DE has 2 members, we have 2 combinations. Okay, now if we take the minimum value out of these combinations, which is out of these 2 values, that means we're using a single linkage. But if we are using the maximum values out of these 2 values, we are using a complete linkage. Okay, so linkage is just a way to represent the distance between clusters, whether we want to use the farthest distance between observations in different clusters, or we want to use the nearest one. Or maybe we want to use the average distance. So we take these 2 values and take the average of it. That means we're using average linkage. Now, there are many types of linkage out there. Another type is word linkage. A word linkage is a variance minimization method. So basically, a new cluster would be added to the existing cluster if adding that cluster can increase the variance the least. Okay, I hope that makes sense. So if, for example, cluster DE add a new cluster B, and the variance of the cluster would be 5, for example. But cluster DE would increase the variance by 7 points if it adds cluster C. That means cluster DE would be better off if it includes cluster B. So depending on what linkage we are using, we will fill in these cells with different values. And once we filled out all the cells in this matrix, the next step is the same. We cluster together the two closest clusters. Okay, basically we need to find the minimum and cluster them together. Well, if you look at it visually, I think we can all agree that A and B are the closest clusters. We can verify this numerically though. So the distance between cluster B and DE must be larger than 3, right? Because the distance between B and D is 3.7, and then the distance from B to E is 4.3. So no matter what linkage we're using, the distance between cluster B and cluster DE as a whole must be greater than 3. And then if you look at it with the same logic, the distance between cluster A and DE, I'll color it purple, would be around 4, maybe larger than 4. And then the same goes with the distance between cluster C and DE. So the cluster C and DE have a distance, around 3. That's the lower bound. But look at the distance between cluster A and B. It's only 1.02. So it must be the closest, and therefore this is the next cluster. Okay, so at the end of the second iteration, we have 3 clusters: cluster AB, cluster C, and cluster D. Okay, let's move on to the next iteration. Okay, now that we have 3 clusters only, that means when we build our matrix, we just need to build it 3 by 3. Okay, and that would be cluster AB, and then cluster C, and cluster DE. To calculate the distance between cluster C and cluster AB, or to cluster DE, we already know how to do that. That's the same as in the last iteration. But how to calculate the distance between cluster AB and cluster DE? Because both clusters have 2 members, right? Well, actually, I already said it before. We just take the combination of all observations in both clusters, right? So now, cluster AB has 2 members and cluster DE has 2 members. So the combination of distances we would have 4 combinations. We need the distance between A and D, which is 4.4, and then A and E, which is 5, and then the distance between B and D, and the distance between B and E. And once we set a linkage, we need to be consistent with that linkage. Okay, so if we already decided to use a single linkage, then in this iteration, we need to take the minimum value out of these 4 values. Okay, so regardless of what linkage we are using, we can fill out, the matrix on the right side. And then the same step happens again. We take the minimum value out of these values in the matrix and cluster them together. And I hope we are all agree that cluster C is closer to cluster AB than to cluster DE. So cluster C would be joined together with the cluster AB. So yeah, the orange cluster here, the orange oval here would be bigger than the oval AB because cluster AB is in the orange cluster. We can also verify that numerically by looking at the distance matrix here, but I'm not going to do that. You can do that on your own. And now, at the end of the third iteration, we have 2 clusters. The first cluster is ABC, and the second cluster is DE. And we're done. Yeah, that's how we saw it, right, earlier. And the agglomerative clustering results is consistent with what we see. Okay, now let's draw the dendrogram. To draw the dendrogram, we start with the leaves. Usually the leaves are positioned at the bottom, but we will see that I changed the position a little bit. I rotated so that the root the root is on the left and the leaves are on the right. Okay, now we have 5 observations, so we have 5 leaves. Let's just draw 5 ticks here. And then at the first iteration, we have cluster D and E together, right? So D and E together. And now this is the important thing. The length of the branch indicates the distance between clusters. So the longer the branch, the farther they are. Okay, but now since D and E are very close to each other, so we can draw a short branch and combine them like this. This means we are clustering them together. Okay, and then at the second iteration, we have cluster A and B together. So the next thing is we write A and B like this. Now A and B is only being merged together at the next iteration, and the distance between A and B is also larger than the distance between D and E, right? So we need to make the branches for A and B longer and then join them together. Okay, and then at the next iteration we have C. So like this, C is the last cluster to be joined. So the branch for C should be the longest. And because we merge it with cluster A and B as a whole, so we draw it like this. Okay, so this is saying that cluster C is closer to cluster A and B together, not to data B alone or not to data A alone, but to data A and B as a group. Okay, now, because at the end of the iterations, we have 2 clusters. So to complete the dendrogram, we draw it like this. And now while we're at it, let's see how we can calculate the clusters. This is the advantage of hierarchical clustering over k-means. K-means is another way or another algorithm for clustering. But hierarchical clustering is sometimes preferable because we don't have to determine the total clusters beforehand. So if you wonder how many clusters do we have right now, we can first cut the dendrogram at whatever distance we want. Oh, by the way, I should tell you this. So as I said earlier, the longer the branch, the farther they are apart. So the y-axis here represents the distance. Okay. Now, back to the total clusters earlier. Let's say that we cut our dendrograms here. Okay, we cut it quite far away from the leaves. The branches that are being cut right away, so right under the place where it's cut, are the final clusters. So we have 2 clusters if we cut the dendrogram at this height. But let's say that if we cut it lower, here for example, that means we would have 3 clusters. The first cluster is DE, and then the second cluster is AB, and the third cluster is C. And there are some formulas to try to find the best place to cut the dendrogram. Yeah, but sometimes it's also a subtractive matter. So, okay, so that's it for the algorithm. Before we go to the coding section, I just want to show you the formal algorithm. Okay, so we begin with n observations, like n is 5 in our case, and we will see that in our application section, n would be equal to 19. Okay, I already talked about that actually in the previous video, because we have 19 precedents over the span of around 100 years. So that's why n is equal to 19 in our use case. But in our example earlier, we have n equals to 5. And then we need a pairwise dissimilarities matrix. This is actually the distance matrix, okay? And then treat each observation as its own cluster. And then we can see here, the for word here is already telling us that this is an iterative process. And the iteration starts with n observations and stops when we have 2 clusters. Okay, so let's go to the coding section now. Okay, so here we are in the coding section. I'm running my code using PyCharm. So first of all, let's look at the libraries that we're going to use for this project. So NumPys, Pandas, and Matplotlib PyPlot are the basic. And then the specific libraries we're going to use for this project, for this video is sklearn and CPI. sklearn, we use sklearn to import the agglomerative clustering, and we use CPI to visualize the dendrogram. And then for tslearn, we use tslearn library to compute the distance matrix. And speaking of distance matrix, this is where clustering for time series is a little bit different from clustering for non-time series. Actually, well, if you have all equal lengths of time series in your dataset, then you can perhaps make it the same as the non-time series datasets. If, for example, you're using Euclidean distance to calculate the distance between 2 time series. But as we will see later, or perhaps if you have seen the teaser video last time, we will see that we have unequal length in our dataset. So the best way, or perhaps the only way, the best to my knowledge at least, to calculate distance between such time series is using dynamic time warping, or DTW. And that's why I need this library. This is going to be the topic for the next video. Okay? Alright, so with that being said, let's move on. This sequence derivative function, I'm going to discuss that in the next video. And then the next function, plot dendrogram. The plot dendrogram function is from the official example from sklearn. But I just modified it a little bit to add the labels and to actually, let's see the function here. Okay, so I modified it to add the labels and to rotate the dendrogram so that the root of the dendrogram would be on the left side. And also add the title. Okay, now the next line here, so from line 40 until perhaps around 66, or until this part. This is the pre-processing data. It's basically how I get the final data. I already talked about this in the teaser video. By the way, before I show you the clustering code part, I think I need to show you the sequences that we're going to cluster. Okay, the time series that we're going to cluster. So these are the derivative of the CPI fluctuation from each presidency. So, for example, Ronald Reagan here. So this is the derivative of the CPI during Ronald Reagan's presidency. And as you can see from the x-axis here, the x-ticks, they don't have the same length. Because some of them became the president for only 2 years, like Warren G. Harding and John F. Kennedy. And then some of them became the president for 4 years, or 1 term. For example, Donald Trump. And then some of them has 2 terms, like Barack Obama. And like Franklin Roosevelt here, he is the only one who became the president for more than 2 terms. Yeah, so we have a lot of variety here. Okay, so let's jump into the clustering part right away. It starts here. Okay. So to do clustering, we first need to instantiate the object. So we just type agglomerative clustering and then set the parameters. There are some parameters provided by agglomerative clustering in sklearn, but these are the parameters that I want to talk about. So the first one is metric. Metric is about how we compute the distances between observations. In other words, how we want to generate or compute the distance matrix as an input to the algorithm, to the clustering algorithm. So here's the thing. sklearn, agglomerative clustering, offers two options. For the first option, we can give the raw datasets of the raw time series, and agglomerative clustering from sklearn will compute the distance matrix for us and also do, of course, agglomerative clustering algorithm. And the second option is to give the pre-computed distance matrix, like we're doing here. So when we give the pre-computed distance matrix, sklearn would just do the algorithm, the clustering algorithm right away. Unfortunately, I cannot give the raw time series dataset to the sklearn because they need equal length of time series, which I don't have, which we don't have. So yeah, pre-computed is the only option for us. Okay, now the second parameter is linkage. Linkage is about what we want to use as a linkage. Do we want to use a complete linkage or average linkage? sklearn offers 4 options: complete, single, average, and the word linkage. However, as you will see in the documentation from sklearn, if we want to use the word linkage, we have to use Euclidean metric. But that's out of option, right? We cannot use Euclidean as our metric. So unfortunately, I cannot show you the dendrogram if we use the word linkage. I can only show you the dendrogram if we use complete, single, and average linkage. And for the next parameter is compute distances. The default value is false, but we have to set it to true so that we can visualize the dendrogram. Okay, so after we instantiate the object, the next thing we should do is to fit it. We fit it to a distance matrix. Okay, since we have set our metric to be computed, we have to give a distance matrix to the fit method. After that, we can plot the dendrogram using plot dendrogram function that I mentioned earlier. And yeah, that's it. Let's run this. So here are the dendrograms using different linkage, like the average linkage here, and then the complete linkage, and the single linkage. Well, if you see in the complete linkage that the branches are colored differently, this has something to do with the distance actually, and we are supposed to be able to modify it, but I just used the default value. So to determine the total cluster, let's say that we want to cut the dendrogram at distance 3, like this. If we cut the dendrogram at the distance 3, we would have 1, 2, 3, 4, 5, 6. 6 clusters, and the CPI series during George W. Bush era and then Joe Biden, Barack Obama, and Donald Trump would be clusters on their own. But if we cut the dendrogram higher, then we would have fewer clusters. Okay, so you can see how different they look. Maybe you will say that, well, the average linkage and the single linkage are quite unbalanced, meaning that there's one cluster that is so big and has many members, while the other cluster has only 1 or 2 members. Now, looking at these 3 dendrograms, we can see that the distance between the CPI of John F. Kennedy and of Lyndon B. Johnson is the closest. It's the smallest, because they always formed first. So these clusters always fuse first into a single cluster, whether it's in average or complete or single linkage. And you can see George W. Bush. So the CPI during George W. Bush era is the last to be included. And that's true for the complete linkage and the single linkage. Okay, now let's focus ourselves on the dendrograms that's built using complete linkage. And as I said before, the series labeled by George W. Bush is the last one to join any cluster actually. So if we want to connect this to the theory section earlier, this is like the cluster C. So cluster C was the last cluster, or like the last data point to get any cluster. And just like the cluster C before, the series for George W. Bush needs to calculate its distance with the big clusters, orange, and the smaller clusters, which contains Barack Obama, Joe Biden, and Donald Trump. Like that. And based on the complete linkage, the cluster, you can say the cluster because George W. Bush was treated as its own cluster, right? That observation or that cluster is closer to the cluster that contains Joe Biden, Barack Obama, and Donald Trump than to the other cluster. That's why it's combined with that cluster. But how they form a bigger cluster after that is quite interesting. So if you see the complete linkage, after merging the clusters from Lyndon B. Johnson and John F. Kennedy, the next cluster to join is the CPI from Dwight D. Eisenhower. And then the next one is Franklin D. Roosevelt. However, if we see the average linkage, the next after Lyndon B. Johnson and Kennedy is still Dwight D. Eisenhower, but the next one is Calvin Coolidge. And Calvin Coolidge is also joined after Dwight D. Eisenhower in single linkage. Again, I'm just comparing the CPI, okay, not comparing the presidents. I'm just using these presidents' name to label the period of time. Another thing that I noticed is that these different looking dendrograms show us how clusters are formed. So for example, like in single linkage, it seems like one cluster is joined with another cluster, and then one cluster is joined again, and then another cluster is added. So just adding one by one cluster. Except perhaps for Gerald Ford and Richard Nixon here, they formed a cluster first before added to the bigger cluster of Harry S. Truman and above. However, in linkage, in complete linkage and average, small clusters are formed first, then they join together. So like in the average linkage, perhaps Lyndon B. Johnson and John F. Kennedy formed a cluster first, and then Dwight D. Eisenhower is added, and then Calvin Coolidge is added, and then Franklin D. Roosevelt is added. Then this whole cluster, this cluster is combined with the cluster of Herbert Hoover and Warren G. Harding. So even though Herbert Hoover is not the president right next after Warren G. Harding, but I guess after several iterations, they are quite close to each other. That's why they form a cluster first. In fact, Warren G. Harding was the president from 1921 to 1923, while Herbert Hoover was the president during the Great Depression, which is 1929 to 1933. So it's like, maybe we can interpret it as, by seeing this dendrogram, okay? By seeing this dendrogram of the average linkage, we can interpret it as the CPI fluctuation in from 1921 to 1923 is kind of repeated in 1929 to 1933. I guess the next question is, What is the best dendrogram? What is the best dendrogram? What linkage could generate the best dendrogram? That's a very hard question to answer. First of all, because there's no one answer that could fit all situations. That's why for every single clustering problem, we need to draw several types of dendrograms using different linkages. Moreover, this is a non-supervised clustering problem. So there's no way we can know which one is the right one. Right. So this is quite a subjective matter actually. But of course there are some attempts to quantify the quality of these clusters. Some of them are like silhouette and devious booting. But maybe I'm going to discuss that in another video. Okay, so in this video, we've learned the algorithm of agglomerative clustering and then apply it to a dataset with unequal length of time series. I guess this is the main challenge of this project because usually when we have clustering or any type of machine learning problem, we always assume that we have the same length, we have equal length of data, but not in this case, and that's actually very common, right? So that's it for today's video. Thank you so much for watching. Please subscribe, share, and give it a like, and I'll see you next time. Bye-bye.